Hello students, in the last video we have seen the quantum theory of normal Zeeman effect, and in that video we have understood how the magnetic field affects the spectra of an element and how it split into three components. A single spectral line is splitted into three components. So now further we are going to study the normal Zeeman effect for one valence electron system. So in 1896, in the initial stages, Professor Zeeman, he was first to study the effect of magnetic field on sodium spectrum. So he has kept a sodium flame in between two pole pieces and he observed the spectra of sodium. You know that sodium is an example of one valence electron system. So atomic number 1 and it has atomic number 11 and it has one valency. So the last electron is responsible, unpaired electron is responsible for producing the spectra of sodium. So since sodium is a one valence electron system, in this video we shall try to understand how normal Zeeman effect affects the one valence electron system, or how one can observe the splitting of single spectral line into three components. So as I have mentioned, Professor Zeeman has kept sodium flame between the pole pieces and he has observed the spectra. Now since sodium is a one valence or single valence electron system, there is a spin orbit interaction. Earlier we have seen this spin orbit interaction, or what is known as LS coupling. Now because of strong magnetic field, this LS coupling is affected. This LS coupling is affected and there is no longer LS coupling existing in presence of such strong magnetic field. While observing Zeeman effect, we are applying the strong magnetic field. So this strong magnetic field for single valence electron system, it is affecting the spin orbit interaction, and therefore whatever the spectra that we have understood for single valence electron system, as an example we have studied their sodium spectra. So this effect can be changed. This effect of spin orbit interaction can be changed because of this strong magnetic field, and you will see that since there is no LS coupling, whatever the splitting of the lines, that will be only because of L vector, that is only because of L vectors. So how, let us see now. So we have to neglect the spin of the electron, and the angular momentum possessed by an electron is given by, as you know, vector PL. If it is representing the angular momentum, PL is equal to L H upon 2 pi. So the orbital magnetic moment is given by mu L is equal to E. These derivations we already solved earlier. So mu L is equal to E LH upon 4 pi m, or this is equal to E upon 2m into PL, because earlier we have seen that this PL is equal to LH upon 2 pi. So if you substitute LH upon 2 pi as PL here, this mu L will become E upon 2m into PL. Okay, so you know that in presence of external magnetic field, this vector L precesses around the field direction, and we have already discussed this kind of precision. This is known as a Larmor precision, and we have also derived the interaction energy by considering this Larmor frequency omega L. So this frequency of Larmor precision omega L, as we have studied earlier, this is given by H into mu L upon PL. So where mu L is a orbital magnetic moment, and this PL, as just we have studied here, the angular momentum vector. So this is equal to, if you substitute mu L here as E upon 2m into PL, so here mu L is equal to E upon 2m into PL. So this PL and PL, that will get cancelled. So this will be simply omega L is equal to E upon 2m into H. Now here this ratio mu L upon PL, it is known as a gyromagnetic ratio. It is known as the gyromagnetic ratio. Now the electron gain additional energy due to this Larmor precession, and this additional energy delta E, it is given by omega L into projection of orbital angular momentum vector along the field direction. So the omega L, you can just substitute E upon 2m into H. Just we have seen the Larmor frequency, and the projection of orbital angular momentum vector on the field direction, that is equal to PL cos theta. That projection is represented by PL cos theta. So this you can just substitute here E h upon 2m, and PL you can substitute as L h upon 2 pi, this angular momentum vector, into cos theta, or this is simply E h upon 4 pi m into ml, where this L cos theta is nothing but ml. We have already seen this while studying the quantum numbers, the orbital magnetic quantum number ml. So ml, you know that it's quantum mechanically we have seen that this ml can take all the values 2l plus 1 values from minus L to plus L. So depending on L, there will be certain number of 2l plus 1 values, number of values of ml. So therefore each energy level splits into 2l plus 1 sublevels with a separation of EH upon 4 pi m, this term EH upon 4 pi m. So L is crucial here. So the spin orbit interaction will be disturbed because of strong magnetic field when you are studying Zeeman effect, normal Zeeman effect, and now only L vector decides. So L value decides this further splitting. So there are 2L plus 1 sublevels, and the separation among these levels is given by EH upon 4 pi m. So let us assume that suppose E1H and E2H are energies of two levels in presence of magnetic field. So we shall consider two situations, when magnetic field is present and when there is no magnetic field. So in presence of magnetic field, let us define two levels, E1H and E2H. Especially H suffix is used to represent that this is the energy level in presence of magnetic field. Okay. So let us assume another situation when there is no magnetic field. So at that time, suppose the same energy level, they are represented by E1 and E2. So in absence of magnetic field, and let the ml values for the two levels are ml1 and ml2. So each of these two level, E1 and E2, they have the ml values ml1 and ml2. So E1H and E2H you can represent by E1H is equal to E1. So in absence of whatever the magnetic field, and in presence of magnetic field, the additional energies because of Larmor precession, and that we can just write here as this quantity. Okay. So E1H is equal to E1 plus ml1 into EHH upon 4 pi m, EHH upon 4 pi m. And similarly you can write E2H, that is equal to E2. E2 is the energy in absence of magnetic field, and due to magnetic field there is an addition of energy, just now we have defined, that is equal to ml2 into AHH upon 4 pi m. So now if there is a transition, then the actual photons given out will be difference between these two energies. So if you take the subtraction of these two equations, E1H minus E2H, so E1 minus E2 plus ml1 minus ml2 into this term will be common, EHH upon 4 pi m. So this is the energy difference, so that is equal to h nu, and E1 minus E2, the original levels when there is no magnetic field, therefore the energy difference E is equal to h nu, you know that. Accordingly this energy difference is h nu 0, nu 0 indicating the original line frequency, original line frequency of the photon emitted when there is a transition from E1 to E2 between these two levels when magnetic field is not present, and this is the transition when magnetic field is present between these two levels E1H and E2H. So that is given by h nu. So h nu is equal to h nu 0 plus, let us define ml1 minus ml2 as delta ml, and this is constant ehh upon 4 pi m. So h nu is equal to h nu 0 ehh upon 4 pi m into delta ml. Now again this particular h you can just divide throughout h, Planck's constant, so h will get cancelled, nu is equal to nu 0 plus eh upon 4 pi m into delta ml. Now again we have this nu 0, the frequency of line in absence of the magnetic field, and splitting will be observed based on the selection rule for delta ml. So you know the selection rule, delta ml is equal to 0 or plus or minus 1, and hence there are three possible lines because there are three different values of delta ml. When 0, nu is equal to nu 0, when 1, then nu is equal to nu 0 plus eh upon 4 pi m, and when delta ml is equal to minus 1, this will be nu is equal to nu 0 minus eh upon 4 pi m. So you will get three lines. These are the three lines. Nu is equal to nu 0, nu 1, we shall define it as the first line with a frequency nu 1, second line with a frequency nu 2, nu 0 plus eh upon 4 pi m, and nu 3 is equal to nu 0 minus eh upon 4 pi m. So they are equally spaced. These two lines, they are equally spaced by an amount eh upon 4 pi m from the original frequency of the spectral line nu 0. Okay, so nu 0 plus this amount, nu 0 minus this amount. So as we have seen earlier, that is suppose delta nu. So now we shall see the actual representation here for one valence electron system. On the left hand side, spectrum without the magnetic field, nu 0, you can see the original frequency when there is a transition between these two lines, okay, these two energy levels of single valence electron system. For the first level, the suppose L is equal to 1, for the second level, suppose this is L is equal to 2. So L is equal to 2 to 1. So the energy difference, that will be h nu 0, and the photon of frequency nu 0 will be given out. Okay, now let us consider the situation in presence of magnetic field. Now in presence of magnetic field, as we have seen here, there can be different values of ml. Okay, so ml can take 2l plus 1 values. So 2l plus 1. So L is equal to 1. Therefore 2l plus 1, that is equal to 2 into 1, that is 2 plus 1, that is 3. So three different values of ml. So what are these values? Plus 1, minus 0 and minus 1. So minus L2 plus L, all these possible values. So there are three values for L is equal to 1. Similarly, there are 5 values for L is equal to 2 according to the formula 2L plus 1, from plus 2 to minus 2. So these are the 5 different values. So from these particular values, so delta ml is important here. So these are the sub levels for this particular orbit for L is equal to 2 and L is equal to 1. So you can say it is p orbital and this is d orbital, L is equal to 2. So you can see now there are three different values here of ml and there are 5 different values of ml here. So you can treat these as sub levels, 5 sub levels, and here 3 sub levels. Now see, there can be further transitions. So you cannot say directly now in presence of magnetic field, just like here there is no magnetic field, we can directly say transition for this level where L is equal to 2 to L is equal to 1. But here there can be sub levels. So 5 sub levels here and 3 sub levels here. So the transition among these sub levels, that has to be considered with the selection rule. For example, the selection rule, delta ml is equal to 0, delta ml is equal to plus 1, or delta ml is equal to minus 1. So this selection rule must be followed while considering any of these particular transition. For example, here all those transition, ml is equal to 0 to ml is equal to 1. So delta ml is minus 1. Again here minus 1 to this 0, again the delta ml is -1, and here -2 to this -1, delta ml is equal to -1. So in this particular transition, according to our relation, nu will be equal to nu 0 minus Eh upon 4 pi m. So this is the line which is having slightly less frequency by an amount Eh upon 4 pi m than the original frequency nu 0. Similarly, the transitions you can see here for delta ml is equal to 0. So the transition for ml is equal to +2, +1 to +1, 0 to 0, or -1 to -1. So everywhere delta ml will be 0, and this will be the original line, the photon emitted of the original line. Original line means, as we have seen, in absence of the magnetic field. And this is the third representation. Here you can see delta ml is equal to +1. Delta ml is equal to +1. If you see any of the transition, delta ml is equal to +2 to ml, delta ml is equal to this +1. So difference is +1. So therefore these three transitions, they represent delta ml is equal to +1, and therefore the according to our formula that we have just seen, nu will be equal to nu 0 plus Eh upon 4 pi m. So this is the line we get in the spectrum with magnetic field, application of magnetic field, where the it is deviated by an amount Eh upon 4 pi m greater than the original frequency. So you can see here a single spectral line is split into three different components. It is split into three different components. So that is how the things are happening in a single valence electron system when you apply a strong magnetic field. And Professor Zeeman has observed this effect first time for the sodium flame. So sodium is a best example of